So here's three examples of the kinds of functions that we're used to seeing so far in this class. And so if you notice, we've got a y value, then an equal sign, and then some number that we often in the past have called the slope, or m, and then plus or minus some constant on the end that we have been calling b, or the y-intercept. So these are some of those. So the first one, m would be 7, b would be 2. This one, m would be negative 1/3, b would be 0, because there's nothing on the end of that one. In this case, m would be negative 1, and b would be 6. Well, there's another way to write these called function notation. So a function notation basically does this. It says it names the functions and it's easily a way to name functions and to easily evaluate them. F of x is read as f of x, or the f is with the parentheses, and you notice I just said it automatically, but f with the parentheses and an x inside is read f of x, and then equals 4x minus 8. And what we're trying to emphasize is this is the same as this, but this function notation version of this equation allows us to do a couple of extra things that is helpful. So first of all, f is the name of the function. This x inside of the parentheses tells us that x is the input. And then this part of the function tells us what it's doing. It's going to take whatever the input is, double it, and then add 3 in this case. So here's an example, pretty quick and easy one. If we have the function f of x equals x plus 9, what would this function give us if we put in for our input 3? Well, that would just be 3 plus 9, so our total would be 12. Pretty darn easy, right? Okay, let's practice a couple more. What would our function give us if we put in negative 3? So negative 3 minus 5. Our function value would be negative 8 in that case. What would happen if we put in 2 for x? So we'd end up with 2 minus 5, which is minus 3. Here's a little bit bigger function. Now, it's got an exponent in it, so this one, if we were to graph it, would not be a linear function, but it's still a function. So let's graph it, or excuse me, let's evaluate it. So 3 times negative 4, and I'm putting that in parentheses, squared, because if this is negative 4, then that means I got to square the whole thing, not just the 4. Minus 5 times negative 4. And what is negative 4 times negative 4? Well, that's 16. So 3 times 16 would give us a number of 48. 5 minus 5 times negative 4, which is negative 20. Oh, what happens when you subtract a negative? You get a positive out of it. So we got 48 plus 20. So our final number there would be 68. And in our last one on this side, we would have 3 times negative 1 squared minus 5 times negative 1. So negative squared would be 1. 3 times 1 would be 3. And negative 5 times negative 5 is positive 5. So our total value would be 8. All right. Not looking too bad, right? Okay, so here's another one. It's a little bit bigger, but we don't mind. So we want to evaluate this function if x is negative 2. So let's put them in there. So 4 And our input for x is -2. And we're going to square it. Then -3 times -2. And then subtract 7 off the end. So -2 squared would be -2 times -2, which is 4. And 4 times -4 would be -16. So our first term would be -16. And then 3 times -2 is -6. So we would have minus -6, subtract 7. Or, to simplify it a little bit further, -16 plus 6 minus 7. -16 plus 6 is -10. -10 minus 7 is -17. All right, not looking too bad. Okay, here's another one. This is a function called g of x. But sometimes they name them differently with different letters. This might stand for how much something grows or gains. So that's what another nice thing about function notation. So we have 2, our input is 0 plus 1. 2 times 0 is 0, 0 plus 1, so our final output in this case would be 1. Okay, what if we have an input of -1? So 2 times -1 plus 1. That would give us -2 plus 1, which equals -1. So for an input of -1, we get an output of -1. Okay, now here we have a graph, and we're told what the x values or the input values are. We're going to try and find the y values. And so it might look kind of daunting at this point, but let's actually take a closer look because it's not really that hard. So let's go to -5 on the x-axis. That would be right here. And then we're going to go up until we hit the y-axis. Or we hit the line, our graph, and then we just see where that lines up on the y-axis is what I meant to say. So look at that. So when you have an x value of -4, you have a y value, or -5, excuse me, you have a y value also of 5. So this point right here is 5, 5, and so we put a 5 right there. I mean a -5, 5 for this point. Okay, for our next one, we're going to go to -3. That's right here. We're going to go all the way up until we hit the top. At -3, we go up and hit the graph, and then turn right, and we find out that we line up with 9. So -3 gives us a y value of 9, or an output of 9. All right, keep it going. How about 2? X value of 2. We go up and hit the graph, turn left and go over and hit the y-axis, and we hit right here at 2, 0, 1. So our y value in this case is 1. And then last, for x value of 3, we go up until we hit the y-axis, turn left and go over until we hit until we hit the graph, I meant to say. Then we turn left and go over until we hit the y-axis. And it looks like a x value of 3 lines up with a y value of 4. So that's how you'll do one of those kind of problems. Just use your input to find the x value on the x line, then go up or down to hit the graph, and then go across till you hit the y-axis and see what it lines up on. Okay, here's a word problem. Let's see how this might work. The graph shows the number of miles a helicopter is from its destination after X hours on its first flight. So use the graph to evaluate the following. So after 0 hours, so here's hours. After 0 hours, we find out that it's sitting at 300 miles away. So that's quite a flight, 300 miles, right? So what happens after 2 hours has gone by? Where's it at? So after 2 hours, we can see that it's this distance away, which corresponds to 100 miles on the graph, right? So what does these mean in terms of the situation? Well, it means that the helicopter is starting out 300 miles away, and then in 2 hours, it's only 100 miles away. So that means that it is flying 100 miles each hour. And so that in 2 hours, it's only going to be 100 miles away. So very nice. So you can, in your own words, you could write that out right there. Okay, here's another one. The graph represents the height h of a projectile after t seconds. So basically, if you're standing up over here and you shoot an arrow into the sky and it goes up and gravity gets a hold of it and starts, well, gravity starts affecting it the moment it leaves your bow and arrow, but it slowly arcs over and falls back to the earth. Okay, so let's just see, and this is going to tell us how high the projectile is after t seconds. So after 2 seconds, how high is the projectile? So we go from 2 up to where we hit our graph. Then we line up on that point and go over until we hit the y-axis, and we find out we lined up at 20. So at time 2 seconds, we are 20 feet above the ground. Well, what about 0.5 seconds? At 0.5 seconds, we're also at 20 feet above the ground. That's kind of interesting, isn't it? So at various times throughout its flight, it goes through the point where it's 20 feet above the ground. So that just means that after half a second, the object is 20 feet off the ground and still climbing. And after 2 seconds, it has already hit its maximum height and started coming back down. And after 2 seconds, it has fallen back down to 20 feet high, the same height that it was when it was 5 seconds into its flight. So kind of a description of it. And so in your own words, you can write that out. All right, so we're going to give you a little worksheet called the function notation worksheet so that you can work on these problems. Thank you very much.